Hi everyone, I welcome you to this new lecture that is 7 on the continuation of mechanical properties of fluids. So one more question I put there and I told that I will discuss on that also given G. So this is the cylindrical vessel that is half filled with a liquid. So that is half filled with a liquid. So when it is rotated, so it will take a meniscus like this. So we have already discussed about this. This is a looks like a half filled and this will become this. So 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 vertically the liquid rises near the wall. So here also when you rotate, okay. So when you rotate it, so the difference in height, there should be a difference in height that came near the wall versus this. So that is nothing but h, and we have already calculated this h to be r square omega square by 2g. Omega is equals to 2 pi f. F is given, that is 2 rotation per second, so that is 2 pi into 2. So h comes out to be 2 pi into 2 square into radius is 5 centimeter. So that is, so we want final answer in centimeter, so we will not going to change. So that is 25 centimeter divided by 2 into 10. Okay. So what we get is 4 was a 16, 16 pi square, 16 pi square becomes 10, 10 will go 8, 8. So it comes out to be 2 centimeter. Check the units. The correct option is 2 centimeter. Check the units when solving this. Okay, so this is all about this concepts of manometer and all. Now, and YouTube. Now I will be going to start new concept that is upthrust and buoyancy. Upthrust or buoyant force. Okay. So upthrust according to Archimedes principle. So according to Archimedes principle, upthrust is the force exerted by fluid on the solid body, or I can rewrite this. Okay, so first I explain what is this. So if you have this container of fluid filled with fluid, the container is filled with fluid. Now you have this body placed on it and it is floating. So but when it is floating, it displays some water, which is equals to the what to the amount that is present in the water. Let's say this height is there. So upthrust, according to Archimedes principle, it feels upthrust equal to the upthrust that is equals to the weight of fluid, weight of fluid displaced. Okay. So now I can write what Archimedes principle is. Archimedes, so it states that the upward force that is exerted by the fluid on the body, on the solid body immersed in it, whether fully or partially, is equal to the weight of the fluid, weight of the fluid displaced by the body. Okay, so that is the fundamental of that is the Archimedes principle. So when this body is float uh, over this fluid, then it feels the force that is in this direction, and that force is equals to the weight of water displaced due to this immersion. Okay, so let's try to calculate upthrust and see what upthrust is actually, or buoyancy, or what is buoyant force. So again, let's take water, and let's say this cylinder is immersed in it. So here pressure is P1, here it's P2, that is H, So we need to make the free body diagram, consider that this solid cylinder is floating in a water, in a bucket of water. So let's call it a bucket of water. Okay. So just by pressure, we know that P2 is P2 minus P1 is nothing but rho GH. Now we need to calculate the force. So net force on the cylinder, which is actually equals to the upthrust. So it is the weight of this body, that is W. Upthrust is acting like this. Let's call it U. That's it. So upthrust is the net force exerted by the fluid to balance this weight. So that comes out to be F2, pressure at this end minus pressure at this, that is F2 minus F1. So that is P2 into A minus P1 into A into P2 minus P1, A into P2 minus P1 is nothing but rho GH. Keep in mind that rho is the density of fluid, not this solid density of fluid, and AH will give you the density, the volume of this body. So that is rho F G V, that is the upthrust in general. So this is the case when upthrust is completely balancing and net force is zero. Okay. Now, generally some question may ask what is apparent weight? Yeah, because it's floating, so W is equals to U. So apparent weight is the weight of a body, the weight of a body in a liquid. So let's say you have this container and here is this tube is there and weight of this is acting downwards, but at the same time upthrust is balancing out it. So the weight, so the exact weight in fluid, let's say that is the apparent weight, is nothing but W minus U. So U actually reduces some weight in water. So it reduces some weight in water and due to the so that's why when you are in water you feel a lesser weight. A floating body feels a lesser weight compared to that in the in general environment. Okay, so that is what we called as apparent weight. So there is a question. It is given that it is given that 1/3 of the volume of solid is immersed in a fluid of density rho f. The density of solid is rho s and mass is m. Calculate the apparent weight. So 1/3 of the volume of the solid is immersed in a fluid. So the water displaced is 1/3 of the volume, whatever it is immersed in the fluid, only that is the amount of volume that is displaced by the solid. So water displaced is, or the liquid fluid displaced, that is U. If the volume of solid is Vs, let's call it Vs, it is not given, that is fluid displaced is Vs by 3. Okay. We can calculate the density of solid, that is, sorry, volume of solid. So mass is m, the volume is, so density is mass upon volume. So Vs is m by rho s. So fluid displaced is m by 3 rho s. Okay, so now we need to calculate the apparent weight. So that is weight minus upthrust. Weight, actual weight is mg. Upthrust is rho of fluid into displaced volume of fluid displaced, that is m by 3 rho s into rho f. Rho f is already there, that is g. So apparent weight comes out to be mg minus rho f by rho s into mg. That comes out to be mg 1 minus rho f by 3 rho s. Okay. So I started the today's discussion with upthrust. So upthrust, according to Archimedes' principle, is nothing but the weight of fluid displaced when some solid body immersed in a water. So according to Archimedes' principle, it states that the upward force that is exerted by the fluid on the solid body immersed in a water, whether it's partially immersed or fully immersed, is equals to the weight of the fluid displaced by the body. So we try to calculate what upthrust is. So we have considered a bucket where we put. So we have considered a bucket where we have filled the fluid, and then a solid body is immersed in it. So it is completely immersed in it. So it means to say that when it is completely immersed in it, so the it will going to displace the same volume of water through the bucket. So we try to calculate what is the upthrust that is acting on this is. So upthrust is nothing but the net force exerted by the fluid on this body. In horizontal direction, if you see, there shouldn't be those forces in both the direction balancing out each other. But in perpendicular direction, there is a pressure difference that is creating a thrust, and this thrust we are we have calculated this thrust to be rho f g into v. V is the volume of the body. Then we have discussed what is apparent weight. So apparent weight is the weight of the body in a liquid. So in a liquid, what will happen? The actual weight is reduced due to the upthrust, because some upthrust is acting on the body. And then we have discussed this question. So it is given that 1/3 of the volume of the solid immersed in a fluid of density rho f. The density of solid is rho s and mass is m. Calculate the apparent weight. So the fluid displaced is nothing but the volume of the solid body immersed in it. So that is Vs by 3. Then density is so we have it is not given what is the volume of the solid. So we have calculated the volume of solid using the density and mass given to that, and then we have calculated the weight, apparent weight, and apparent weight is nothing but the actual weight minus the upthrust. So actual weight is mg. So that is mg minus the upthrust. So that is this. So the solution to this is this. Okay. I hope you understand this. So now let's look at the law of flotation. So law of flotation means to say that we have a container. Let's say we have a fluid, and now we have this fluid, and then a body, some solid body is there that is floating in it. The question is when the body will going to float in this uh, fluid. So the question is when the body will going to float float in this fluid. Okay. So according to me, if you think that in a very general way. So there should be a force that are balancing out each other, and this will come in a static equilibrium, and then that's the only condition when it is floating. So what does it mean that? So if you have a fluid and you have this solid body in that, so it can only be floating if if it is at equilibrium. Means to say that net force acting on it is zero. The net force acting on this body is zero. Then only it is it gets float. In a general case, if let's say this case, what we are looking at now. So in this case, body will float if weight is equals to upthrust. So that is the law of flotation. But if you let's say tie this with some spring, so there are other forces. We need to balance out those forces to get to know the condition and whatever the question is there. I will be going to discuss those questions uh, in coming slides. So let's take first question. So cylinder, a cylinder of length L is floating inside floating on a water in a bucket such that 1/4 of its length immersed in water and remaining will be there in air. Calculate the density of solid if density of fluid is 1000 kg per meter cube. Okay. So let's say you have this bucket. For any question, if you want to go and do you want to solve that question, the best way to approach any question is try to see what the question is. And the way you see the question, what is the question is, uh, you have to draw a figure for it. And if required, free body diagram of it. So there is a water. This is the cylinder. So that is actually L by 4 that is immersed, that is given 1 by 4 of the length is immersed in water, and remaining that is 3L by 4 is in air. 3L by 4 is in air. Raw water is 1000 kg per meter cube. We need to calculate the raw solid, and it is clearly mentioned that it is floating. When it is saying floating, it means to say that weight of this cylinder is equals to the upthrust. Okay. So weight of this cylinder is nothing but rho solid area into length is equals to upthrust is upthrust according to Archimedes principle, the water displaced due to this emulsion. So at is as it is immersed in the water, so L by 4 of the length into area, that is the volume. So volume get displaced from this container. So the volume displays this A into L by 4. So that is A into L by 4 into density of fluid into G. So from here what we get is rho S. A is this area, so A is same. L will cancel out each other. So what we get is 1000 divided by 4. So that is 250 kg per meter cube. Okay. So let's take another type of question. So I will make a figure. So an iceberg of density 0.9 gram per centimeter cube floats on a sea having a water density 1.1 gram per centimeter cube. Find the fraction of ice. Now we know the density. Find the fraction of ice which is visible to a ship at sea level. So in the question it is saying that there is an iceberg that is floating over a water in an ocean, and there is a ship who is looking at that iceberg. So what fraction of iceberg is actually visible to the ship? So that's the question. So let's say if this is a sea, so the fraction of ice which is visible to ship is that fraction that is in air. Fraction of iceberg that is in air. Okay. So if it is, let's say this is a sea, and let's say this is a big iceberg. So let's say X part of it is visible. So we need to calculate X. Total length, let's say, is L. So we need to calculate the fraction of iceberg that is in air. So X is visible. So what we need to calculate is the fraction. Fraction means how much of the total part. So that is X by L. We need to calculate. Okay. We know the density of uh, iceberg is 0.9. Again, it is floating. So according to law of flotation, weight is balanced. Weight is going to be balanced by F thrust. We know the density of fluid. We know the density of solid, and then we balance out each other. So what we get is, let's balance. So weight of solid is complete weight. So that is rho solid into volume of solid. That is A. So this cross section area, consider it to be A. That is A. Consider it to be A into L into G. And upthrust is the weight displaced by it. So what is the weight that is displaced by this solid? Is L minus X into A. So water displaced here is L minus X into A into rho of fluid into G. So from here, what we get is L into 0.9 is equals to L minus X into rho of fluid. Rho of fluid is 1.1. So L minus X by L comes out to be 0.9 divided by 1.1, and what we need is X by L. So 1 minus X by L is 0.9 divided by 1.1. That is 9 by 11. And X by L comes out to be 2 by 11. So the fraction that is visible to a ship is 2. If the length of, what it means is, if the length of this iceberg is, let's say, 11 centimeter, then the visible part is just 2 centimeter to the ship. So in Titanic, collided, the ship was collided with the iceberg. So that's why it's important to calculate it correctly. Okay. There are very interesting questions, and this topic is very important for JE also. I have seen many questions in JE. So I have time for one more question. Let us discuss one more question, and rest we will discuss tomorrow. This is a very important topic. So we need to calculate So there it is given that, so there is kerosene and oil present. This question was even asked in GATE. Simple question, but so this is a cube that is floating at the interface of kerosene and water. Density of water is 1 gram per centimeter cube given. Density of kerosene is 0.8 gram per centimeter cube. And this is ice whose density is given as, the density of ice is 0.9 gram per centimeter cube. Okay. So it is floating at the interface of kerosene and water. So the ice is floating at the interface of kerosene and water. Calculate the ratio of length of ice which is present in water to kerosene oil. Options are 2 is to 1, 8 is to 1, 1 is to 8, 1 is to 1. So what we need to do is it's floating again. So its weight is balanced by the upthrust. But now there is two upthrust. Upthrust by kerosene plus upthrust by water. Now there is two upthrust that is balancing this. That is by water and kerosene. So weight is rho, volume let's say is V into G, upthrust by kerosene. So let's say X part of it is in kerosene and Y part is in water. And area is A. So A into X into density of kerosene into G. So that is volume of kerosene displaced. This is volume of water displaced. And net volume is X plus Y. This is ice. X plus Y into E. So A will cancel out with each other. So rho of ice is given 0.9. G will also cancel. 0.9 into volume is X plus Y. This is X into rho K, that is 0.8 plus Y into water is 1. So 0.9x plus 0.9y is equals to 0.8x plus y. What we need to calculate is x by y. The ratio of length of ice which is present in water to kerosene oil. Sorry, y by x. We need to calculate y by x. So it comes out to be 0.8. Is there any mistake corrected? So volume is x plus y into a, and that is 0.9. Okay, it's correct. So 0.9x minus 0.8x. So that is 0.1x and that is 0.1y. So y by x will be 1 by 1. Okay, the correct option is this. So I will be giving one question that came in J. Try to solve it and we'll discuss it tomorrow. So there is a spring. Okay, so just putting this question there and then, so here it's a spring and a spring block system that is floating in the water. The radius of this is 3 centimeter. Height is 10 centimeter. Density of block is 8,000 kg per meter cube. Force constant is 1000 Newton per meter. Density of water is kg per meter cube. Question is find the elongation in spring. Okay. Okay. So we'll discuss in the start of next class.